Hello, and thank you for attending this public webinar where I would be discussing about the experience of Masi, a mechanical ventilator developed and clinically implemented during the COVID-19 sanitary emergency in Peru. My name is Fanny Casado, and I work in the Pontificia Universidad Catolica del Perú. The experience that we had to develop Proyecto Masi started because in Peru, healthcare services are overcrowded even during interwave periods. And when faced with the insufficient resources of COVID-19, we decided to take action and start building a new ventilator that whose experience I'm going to be detailing today. Some of the problems that we were dealing with at that point was restricted space for inpatients, poor oxygen supply, lack of ventilatory devices, and also not enough intensive care unit or the team of different healthcare staff that is needed to respond to this type of emergencies. We know also that 29% of COVID-19 patients were developing this acute respiratory distress syndrome that require a prolonged mechanical ventilation to survive while the lungs were going to be recovered. Also, at the beginning of the pandemic, what happened is that commercial trade of mechanical ventilators that were being manufactured in Europe and USA obviously were prioritizing their own local populations. With all that, we also had to face the fact that the regulatory bodies in Peru have no experience and they couldn't provide any guidance on how to evaluate Peruvian-made medical devices. So in order to develop a ventilator that could be used during these critical times, we set up a chronogram that was actually very exhaustive, but that I think it was required and critical in order to truly have a response during this time. We started in March 2020 with the design and all of the different prototypes that were developed until July 2020. Then the time of production started, and finally from January of 2021, clinical deployment and close follow-up was done in this 6-month period. From then, some of these ventilators are still in clinical settings, and we are still collecting data for technovigilance. So how is it that this started was based on some academic exercises that were previously described in order to generate a new mechanism of action where, as you can see here, a mechanical paddle actuator would press on a resuscitation bag, and this bag will be filled with oxygen that was directly coming from a bottle of oxygen. And this was really important for us because the flows that usually come from bottles of oxygen are a little bit lower than what you would get from the lines that are usually present in hospitals. So we didn't have those lines. So the best options that we had was, first of all, to receive oxygen from bottles. And therefore, this ventilator was designed having that in mind, that the oxygen supply would be limited and that we needed to the best of our knowledge, be able to save as much oxygen. And therefore, this bag that will be activated by a mechanical paddle would need to also collect and have very small number of leaks in order to then pass through oxygen sensor and then through a flux and pressure sensor before it would enter into the airways of the patient. Obviously, all of this was going to be controlled by a control unit that was also developed and printed in Peru. And all of this information has been published already in HardwareX, which is an open source type of magazine that promotes precisely the publication of novel and innovative approaches in the sense of hardware that can be directly used and built under different circumstances that will not follow the classical models of commercialization of devices. So another aspect that was also important for us was having telemetry. So besides this novel mechanism of action that was relatively simple, as you can see here, it was basically what we usually call an AMBU bag. It is actually a resuscitation bag that can inflate and deflate with these paddles. And that is what is shown here on the diagrams. And then here on the pictures, we're also showing a very important part of this effort, which was to develop a multi-platform telemetry system, because we were aware, as we told you before, that we had a relatively small number of specialists that would be able to follow up all of the patients that we're expecting that we would be having to deal with. Also, in this HardwareX article, we describe all the technical specifications that we needed to accomplish in order to test the different prototypes, such as, for example, electrical safety. Besides electrical safety, we were also able to show that the technical characteristics and performance assessment was positive. That means that this ventilator, when we measure parameters regarding the three ventilation modes that we were proposing to have, will actually have in ranges that would be the expected ranges and what would be part of the standards for this type of instruments. So basically, as you can see here, the accuracy of measurements was in all cases the variability was lower than 50%, in some cases even lower than 10%, which was a really good performance for this type of instruments. All of these quality control and technical assessments was actually done in a special environment that we developed in our university, where we were able to implement a chain where quality control will be done. Also, with once we already knew that these prototypes were actually up to this, following the standards, and they were being able to meet all the expectations and the characteristics that were initially set up for them, we proceeded to ask our ethical board committee for permission to perform a preclinical analysis. The preclinical study was done using production swine. That means they were not laboratory animals, they were actually production animals. And we were able to publish that in the journal PLOS ONE, as you can see here. So basically, the design of that experiment first accounted for the fact that we were using a model that was not quite completely defined as a model. Nevertheless, since they were pigs used in production, there was a lot of information about them. And we also showed them because of the volume, the tidal volume that these type of pigs have is equivalent when they are weighing 40 to 60 kilograms, will be equivalent to a 70 to 100 kilos person, right? Which will be about the standard in Peru for the Peruvian population. So after we set up a preliminary study in order to evaluate different parameters of how to sedate the animals and prepare them for the mechanical ventilation, we decided to perform the preclinical trial in 2 steps. First, we performed experiments in 4 animals, then we studied the results. Because we did not observe post-mortem evidence of damage, then we continue with another 4 animals in order to have statistically relevant results that we could publish. And as you can see here, it was very important for us to have a good setup of the different drugs that needed to be used in order to warrant that these animals will not suffer with this type of experimentation. For these purposes, we intubated the animals, and then also they were obviously they were sedated, but then also they were exposed to the ventilation with this with Masi. First, with mandatory for for the total of 6 hours. From that point, first they had mandatory ventilation, and then they have the last 10 minutes, it was triggered ventilation. That means that during that time, it would be the patient, the pig that was that we were taking out a little bit from the sedation. They would be able to stop share.
Hello, my name is Adriana Téllez, and I'm going to talk about non-invasive glucose measurement. The importance of blood glucose measurement lies in its relationship with one of the most important diseases today, diabetes. Under normal conditions, the body takes energy from food. The pancreas generates a hormone called insulin, which is responsible for taking glucose from food and transforming it into energy for the body. However, diabetes is a chronic disease characterized by the fact that the body does not produce enough insulin or does not use it properly, causing the blood glucose levels to rise. There are three main types of diabetes. In type 1, the body does not produce enough insulin. It is considered an autoimmune disease since the body itself attacks the cells that produce insulin, affecting its generation and causing glucose levels to rise. This type usually appears in childhood, but it can also occur at any age. In type 2, the body does not properly use insulin. This type can be due to multiple factors, such as inadequate food intake or overeating, which causes obesity. Another factor is a sedentary lifestyle, that is, not doing enough physical exercise. Type 2 can also have hereditary factors. Normally, overeating causes a greater amount of insulin to be generated until the body cannot generate more and cannot use it adequately, causing an increase in blood glucose levels. Type 3 is gestational diabetes. This is a temporary condition that occurs during pregnancy. However, if a woman develops this condition during her pregnancy, she should be continuously monitored as it can lead to permanent diabetes. It is important to note the increase in diabetics in recent years. In the year 2000, there were 151 million people with diabetes in the world. In 2014, it was estimated that by 2021, there will be 333 million diabetics. However, by 2021, this figure was actually 200 million more than the estimated amount. That is, 537 million people suffered from diabetes in 2021. This is 1 in 10 people with diabetes between 20 and 79 years old, of which 3 out of 4 belong to low and middle income countries. In addition, it only considers the diagnosed people. It is necessary to take into account people that has diabetes but do not know it. The number of deaths associated with diabetes has also increased considerably in recent years. In 2014, 1.5 million people died from this disease, while in 2021, the figure rose to 6.7 million people. These statistics are taken from the World Health Organization, which considers diabetes to be the seventh leading cause of death worldwide. During the life of a person with diabetes, they can develop multiple associated diseases, such as blindness, kidney failure, amputation of limbs, heart attacks, and strokes. It is also important to consider the economic impact of this disease. For example, in North America, in 2015, the cost of diabetes was $348 billion, and this figure is expected to increase to $390 billion in 2040. This figure does not only correspond to the treatment of the disease, but also to the fact that people with diabetes are less productive and receive less income for this reason. However, diabetes is not necessarily a fatal disease, nor should it have important consequences for people's health. Through constant monitoring of blood glucose levels, it is possible to take appropriate actions that allow adequate control of the disease. Hence, the importance of blood glucose measurement. In one of their classifications, glucose measurement methods can be divided into invasive, minimally invasive, and non-invasive. Invasive methods are the ones that require a blood sample to measure blood glucose levels. Those are the use in laboratory tests and in the traditional glucometers. They usually require to puncture the patient's skin, normally in the patient's finger, to take a blood sample. This drop of blood is placed into the reactive strip, inserted into the device to estimate glucose levels. These methods are highly reliable and they are very convenient when the patient only requires one or two measurements a day. However, children or elder people normally require, because of their metabolism, more measurements. They can require up to 10 measurements a day. That means that they need to be puncturing their finger, and this can be really uncomfortable or even painful for the patient. Besides, there is a risk of infection that makes these devices not viable for continuous measurement. An alternative are the minimally invasive methods. They use the flash system. They also require a puncture in the patient's skin, but it is only a puncture for each period of useful life of the sensor, and this puncture is performed by microneedles as the measure in the interstitial liquid. They are also highly reliable, but there's still a small risk of infection. Besides, the sensor normally has a high cost. On the other hand, non-invasive methods perform indirect measurement of blood glucose using the properties of glucose to estimate the glucose levels. There are several techniques used to perform non-invasive measurement, such as ultrasound, electrical impedance, and spectroscopy. There are several projects intended to perform non-invasive glucose measurement. One of them is ILA. This method consists in a band that contains sensitive physical sensor. It measures glucose in sweat. A drop of sweat is placed into the sensor, and the device estimates the glucose levels. It has an application that helps the patient monitor during the day the glucose levels. However, as the sensors need to be replaced continuously, it can be a little bit expensive. Another project is hermetic. It measures specific gases corresponding breathing and skin vapors, considering that the increase in glucose levels changes the composition of these gases. Another project is GlucoWise. It uses low-power radio waves and measures the capillary response to these waves. This response is associated to the glucose levels, so it can be estimated indirectly. Another project is the Pocket. It uses a light wave. The light causes a temperature change that can be associated to the glucose levels. At the Instituto Tecnológico de Morelia, we are also developing a non-invasive glucose measurement device. We have analyzed different techniques in order to select the one that has a better performance to this aim. One of the analyzed techniques was the reverse iontophoresis. This technique consists in injecting a constant current to the skin through electrodes that contains an enzyme that reacts to glucose levels. This method has as advantage that it's accurate and it has an easy implementation. However, it requires warm-up and it can irritate skin. Besides, it is sensitive to perspiration and needs constant recalibration. Furthermore, it is insensitive to rapid change in glucose levels. Another analyzed technique was the electrical Bio Impedance. It consists in injecting a current flow that corresponds to a known voltage that allows calculating the impedance in the body. This impedance can be related to the blood glucose levels. This technique has the advantage that is sensitive to abrupt changes. Besides, it is efficient in states of hyper and hypoglycemia. However, as a disadvantage, it has a low accuracy and it's very sensitive to external factors such as perspiration and humidity. Another analysis technique was the electrochemical sensing. It uses enzymes that react to glucose, allowing to measure the glucose levels in the patient. It has the advantage of high portability and high accuracy, but it requires a periodic change of sensors and is sensitive to external factors such as perspiration and humidity. Another technique is the photoacoustic spectrometry. It requires multiple sensors because it uses sound and light. The response to these variables can be associated to the glucose levels. It has the advantage of high sensitivity to small change and high specificity, and it only requires one calibration per user. However, it requires multiple sensors working simultaneously, and it's very sensitive to moisture concentration in the body. Another technique is the infrared spectroscopy. It consists in sending a light beam to the skin. The light is into the infrared region and the response is measured and it can be associated to blood glucose levels. It has the advantage of a high portability and it has no reaction to patient fluids. As a disadvantage, it is sensitive to artifacts present in the skin and it's also sensitive to external light sources. The selected technique was the infrared spectroscopy, specifically the near-infrared spectroscopy. That is because the light in the near-infrared region has a specific response to glucose that can be used to estimate blood glucose levels in the patient. However, as an optic method, it has problems associated with the need the blood capillary response of the patient. And the light needs to travel through several layers of the skin that affects this measurement. Some of the factors that affect the blood glucose measurement using near-infrared spectroscopy are the physical and functional parameters of the skin, such as fat, temperature, skin tone, and humidity. Besides, using specific devices to measure all these factors in order to compensate their effect in the glucose measurement can increase the cost of the device. Our methodology consists first in performing the optical measurement. The obtained signal is filtered and amplified in order to be used in the digital signal processing stage, where it is characterized in order to obtain a model that includes the compensation of the different factors that affect the glucose measurement. Once the model is obtained, the blood glucose estimation is performed. In order to obtain a reliable model, an statistical analysis was made. The analyzed variables were systemic arterial pressure, weight, BMI, and body fat percentage, liquid fat percentage, body temperature, and oxygen saturation percentage. A correlation analysis was made in order to determine which of the analyzed variables affect the blood glucose measurement in order to include them into the model to compensate their effects. The obtained mathematical model includes the measurement of the sensor corresponding to the near-infrared measurement, the IMC, the arterial pressure, the body temperature, the skin tone, and the fat percentage. However, as we need to measure all these variables in order to compensate their effect in the glucose measurement, to avoid using commercial devices that perform every specific measure, we decided to correlate optical sensor at specific wavelengths that could estimate these parameters. The selected wavelengths, considering the AC and DC components, were 940, 660, and 515 nanometers. That allows obtaining a compensated model that was validated by using a commercial glucometer with high accuracy. In order to validate the obtained results, the Clark's error rate was used. In this rate, it is considered that if the measurements are in the A regions are adequate, in the B region they has more than 20% of error, but it is not a problem. If they are in the C, D, and E regions, the measurement is inadequate. In our model validation, 96% were in the A region and about 4% in the B region. In conclusion, non-invasive blood glucose measurement is factible. Depending on the selected method, continuous measurement of blood glucose can be performed. By including some specific devices and protocols into the non-invasive glucometer, data can be available remotely. Using an application, we can generate alerts according to the blood glucose levels. In fact, this continuous measurement, this alert generation, this data availability allow us to monitor the blood glucose levels, and knowing them, we can control diabetes, improving the life quality of the people. Thank you very much for your attention.
Welcome everybody. Welcome to this short presentation about the use of artificial intelligence for tuberculosis diagnosis support in demanding scenarios. My name is Álvaro David Orjuela-Cañón. I am Associate Professor with the Universidad de Rosario inside of the School of Medicine and Health Sciences. Now I am volunteer of the IEEE here in Region 9 and the Colombia section. Currently I am working on with the EMBS chapter in my local chapter here in Colombia, in Bogota, Colombia. Now, the agenda for this short presentation is first an introduction about the problem that we are dealing with the use of artificial intelligence. For this, I show you some preliminary concepts about artificial intelligence, not just sophisticated definition, but I think that is necessary to understand how we are working with this kind of technology. In fact, we are working with artificial neural networks, and I'll show you two kind of neural networks to develop the diagnosis, to support the diagnosis. And then I'll show you some examples that how we are working with AI and tuberculosis. At the end, I will show you some final comments that we are discovering with time and working together with physicians and health professionals that are interested on this topic. First of all, you can see that, or you can think that tuberculosis is not a present problem in the world, but there are many countries, especially countries in the developing countries area, for example, Africa or South America, when you can find high incidence rates. It means that many people has the disease, and it's important to detect and treat these people to have a happy end of the disease. The World Health Organization has the strategy NTB. The idea here is a program that to eradicate this disease by the 2035. So any effort in this field is important to contribute to eradicate the disease. Okay. About the tuberculosis, you know, the most popular tuberculosis is the pulmonary tuberculosis. It's a disease that attacks the lungs based on the Mycobacterium tuberculosis bacillus. It enters the body, but can affect any part of the body. So the most common is the lungs. So here you can find a respiratory disease, but we can find extrapulmonary forms of TB. Okay, the first or most common is the pleural tuberculosis that this affect the serosa that is covering the lungs, and it is difficult to detect this disease. And another form of tuberculosis is the meningeal tuberculosis. Is a lateral disease. If you don't detect at time this disease, it could be a problem because it causes the death, or could causes neurological consequences. What is the challenges about this of the diagnosis of these three forms of TB? First of all, the pulmonary TB has problems associated to resistance. The treatment to deal with TB is based on the antibiotics, but people don't complete this treatment. So this causes that the bacillus generates resistance to this kind of medicaments, and it's difficult to treat or to detect. So many tools, many new techniques are necessary to detect this new form of pulmonary TB. In terms of pleural TB, is a painful, invasive, or more expensive procedure. It is necessary a thoracentesis where you need or you extract some pleural fluid or pleural tissue to the culture and see if the bacillus is growing with time for detecting the disease. But you can see that it's difficult to do. So if you find new tools and new alternatives to the diagnosis kind of this form of tuberculosis, based on AI, could be an extra help that can be provided to the health professionals. The meningeal TB is a similar case where it is necessary to extract some cerebrospinal fluid from the body and to do some molecular tests, for example. But the idea is to avoid this kind of procedures and obtain similar results in terms of detection. Okay, what is the proposal? What are working on this? First, I show you some concepts about the artificial intelligence, where we can define the artificial intelligence as a bio-inspired systems. If you see the Computational Intelligence Society, they show that there are three main paradigms of the artificial intelligence. First is the fuzzy logic, that it relaxes the concept of the traditional logic, and it allows to communicate between machines and human beings. But maybe the most important thing about fuzzy logic is the uncertain that you can define so many processes or systems based on classification of variables, and determine so many rules based on the specialist to deal with any problem that is difficult to deal with traditional techniques. And additional, you can find the artificial neural networks. I think that is the most popular concept about artificial intelligence. Some people think that artificial intelligence is just neural networks, but we can find many different forms of artificial intelligence. For example, you can find swarm intelligence, which is similar are colonies or animals, so many intelligence that you can find in group, a collective intelligence. It's not just neural network. So, but here I concentrate our attention in the artificial neural networks. And just to complete the context of the artificial intelligence, you can see that some machine learning is a set of models based on a statistical learning, where they learn from data. Here you can see the artificial neural networks, but there are more models like support vector machines, random forests, and so on. You can see an example, small neural network, but you can find bigger neural networks. There are no that deep learning, but now here you need huge quantities of data to train these kind of models. Okay, there is a transfer learning, but there is no option if you don't have enough information or enough data to train these models. If you see the basic concept about artificial intelligence is the artificial neural networks is the neuron. Here you can see a neuron with dendrites, the axon, any biochemical process inside it, and in bottom you can see the artificial unit or artificial neuron. It's the same concept. You can see the dendrites. It's a computation of these weights associated to a neuron, and finally you can find a nonlinear activation function. Okay, when you have the unit, you can connect them and propose architectures like in the left side, and you can see that there are the most common architecture that is a multi-layer perceptron. Here you can find 3 or 2 layers, one hidden layer and one output layer. And the idea here is to train the model to classify or to do a regression about based on the input variables. Here, the supervised learning is understanding that the supervision of the how the error is reducing with the time. Meanwhile, the neural network is learning. To the other side, you can see the unsupervised learning with neural networks that learns about the similarities between data. Now I work in some examples. I showed you some examples. Here, the idea in traditional machine learning is to do a feature extraction. This because you can establish different sources from data. For example, you have information from biosignals, from questionnaires, from signs, symptoms, in the consultation. You can find information from sequences, from DNA or proteins. Establish a model that is a neural network to provide information or extra help to professionals to make a decision about the treatment, about the detection, about the decodification, for example, the coding, or any kind of task that is necessary with this kind of models. For us, the idea is to show you some examples in demanding scenarios. It means that you don't have enough infrastructure, equipment, you don't have sophisticated laboratories on data. No? You know that to train neural networks is necessary data, but sometimes you don't have that. The idea here is to show you some examples about this. The first case is it's a problem that we worked with some health professionals inside of the Hospital Santa Clara here in Bogota. Is the most known institution of patients related with tuberculosis. The idea here was design, obtained a neural network that was trained with data from this institution. This is important to show you because there are no enough data. They have in mean 100 patients by year, so you don't have huge quantities of data. But the idea here is to provide some example of how we are working with the neural networks and these demanding scenarios. The idea here also is to use just 7 variables in a preliminary pre-diagnosis. And the idea is to embed this model and to send you another regions in Colombia to provide an extra tool for to do the diagnosis. The idea was to train this neural network to detect the TB. In this case, a patient suspicious to have TB. He is present in the institution, and then it's begins the protocol to diagnose the TB. Another example is to use supervised learning in the time series application, where the idea here is to do a forecasting, time series forecasting, based on this non-linear autoregressive model. The traditional modeling in the time series is based on the autoregressive models. Now we are introduced to non-linear autoregressive model based on the non-linear function activation function in the units in the hidden layer. The input is some lags from the input. Now, or you can see here a time series of the new TB cases week by week in Bogota, Colombia. This work employed a neural network to do the forecasting. You can see this period of time and the prediction. You can see the red and blue lines that were forecasting of the time series, employing non-linear autoregressive model and neural network, a recurrent neural network long-short memory term that which is it has the capacity to learn from long and short term to store in memory. The idea here is provide this forecasting for authorities, local authorities, for example, institutions or authorities in the city, the health of the city, to plan any actions to deal with this number of cases of TB. Here, in the case of the pleural TB, you know, this procedure to for diagnosing, you need to do this procedure, this painful procedure with the extract the fluid or tissue from pleura. The idea here is avoid the liquid culture because you don't need. The idea is to avoid this information because you can obtain the similar rates to detection with another variables. For this, we are using a self-organizing map that dissemblate the information as a cortex does. You know, any different region of the brain is activated by different senses. So the idea here is to represent the senses like 3 risk groups. We have high, medium, and low risk groups. Here we can see how the map, how the neural network, how the neurons are activated by the input vectors from information with patients with the disease, with TB. You can see how this information activate the red and yellow regions. And for people that is suspicious to be tuberculosis, but without the disease, because at the end we have the gold standard that is a procedure based on culture of the bacillus. The idea here is to see how the input vector of the information activates the different regions of the map. So now this could be useful for professional health that can see how the information from the patient is associated to different zones of the map. This could be useful when you have a management of the patients. In addition, you can find the nonlinear correlation between the input variables and the regions. For example, you can see how the ADA, ELISA, and PCR could be directly related to the high and medium risk. Next, the idea is contribute in different sources of information. We can find laboratory information, clinical information, medical images, and medical records. And here we are working with natural language processing to extract information, important information, to could be useful in the diagnosis process. Many words are worked, but medical images and deep learning models. But now is not our case, because I said we have problems with data. We don't have enough data to train the models. And the idea is to do a preliminary detection. If you tries to do this with this kind of images, it's difficult because there is no issues on the image. Just I put this information to compare how would we did. If you search in the literature, you can find many applications about this. Okay, just to end the presentation, what is next? We are working with natural language processing on medical record. provide or to extract important information that could be help in other places far from cities when the precarious scenario is all you can find around you. In addition, now we are working with drug discovery, for example, deal with databases based on the components and cheminformatics and how these any previous assays that they are reported in these databases could be useful to design new medicaments and new drugs for this kind of disease. Just to end the speech, I have to say that AI could be relevant for propose some new alternatives and strategies against the problems related with health systems, for example, TB. It's important to do interdisciplinary groups. You need to work together with the health professionals. They will use the technology, and it's important that they work in a unique way. AI can contribute in different phases, in preliminary, advanced, and so on phases of the disease. Maybe we can contribute to vaccines and drugs discovery, as I mentioned. And now we are working with the dilemma between data and personal information. That it is difficult to extract data, the ethical committee and so on, and things like that did not allow to go beyond to determine or new tools. And interpretation of AI models that it is necessary to understand how it's working or how it's happening inside of the models. Okay, thank you so much. There are some reference when you have some details about this result that I show you. So I have to enjoy it. This is my contact. If you have questions, please just contact me, and I'm happy to answer your questions. Thank you.
Hello, my name is Gilberto Ochoa Ruiz. I'm research professor at Tecnológico Monterrey, working in an advanced AI group, and I'm the leader of the CV Computer Vision Insight Lab. Basically, I'm here to present you my work using endoscopic images of kidney stones, titled "Show Me Your Stone, I Will Tell You Who You Are," towards automatic classification of in vivo urinary calculus using computer vision techniques. This is a work we have been doing in collaboration with the Centre de Recherche en Automatique de Nancy in France and the University of Lorraine. So the presentation will proceed as follows. First, we'll start with some medical context to understand what the importance of the kidney stones identification is, what opportunities for using machine learning in this context are, then some of the state of the art, like basically which are the current practices and some of the opportunities to help to automate this process and to make the process for the patient better. Then we'll talk about a little bit about some of the work we have been doing towards the automatic classification of kidney stones using deep learning, and we'll discuss some future work. So as you might know, kidney stones are a very big problem. Actually, we always heard about people suffering from kidney stones, and it's a very painful thing to have. The formation of these kidney stones is called urolithiasis, and it's basically the formation of these kidney stones in the kidney, ureter, bladder, and urethra, and it's very common disease around the world, and it's only expected to increase with global warming and climate change. Some of the common formation causes are the diet, also hereditary, urinary tract infections, and the consumption of certain medicines. And depending on the lithogenesis or the origin of this formation, the doctor will have to diagnose this and prescribe a treatment. So it's very important to have a timely and accurate treatment in order to avoid future relapses and to avoid pain for the patient as well. So basically, for identifying kidney stones, they have to see where the kidney stone is located using a combination of CT scan and X-ray techniques. With this information, the doctors will use this information to plan how to extract the kidney stone. Basically, they have to do the operating room. They have to use CT scan X-ray to identify what the stone is, to find the best way to introduce an endoscope. There are many techniques, but the most important are shockwave lithotripsy, using sound to pulverize the stones, which is a much traumatic way of doing it. And the other one is laser lithotripsy, in which they introduce a laser, and the laser can be either external or internal using an endoscope. The laser lithotripsy is the one that is becoming more common because it's less invasive and less painful for the patient. Once the stone has been removed, the second step is to use a combination of polarization microscopy and infrared spectroscopy to determine the chemical composition of the kidney stone. So basically, the doctors will use information of the surface and section of the image, what is called the morphological information, as well as the chemical composition to determine which was the cause of this formation, or the lithogenesis of that formation. This morphoconstitutional analysis has been proposed by Michel Dodon, a French doctor, which with him we have the pleasure of collaborating in this project. And he has been working for several years proposing different tables, different ways of analyzing kidney stones. Basically, you have to analyze the surface of the kidney stones, the section of the kidney stone, and also in combination with the biochemical analysis, you can determine what the causes of the formation. So it's very important because it's a very robust diagnosis, has a very high value for diagnosis, and has the benefits of drawing individualized treatment plans. However, it's very difficult to use because it requires a lot of training, and it's very difficult to translate to different persons, basically. So the idea is how can we automate this process, and this kind of the motivation for our work. Basically, as mentioned, the morphoconstitutional analysis uses the microscope and the infrared spectrophotometer in order to try to determine, basically analyzing the stone under the microscope to determine the characteristics, morphological characteristics of the kidney stone. But this is, as I mentioned, very time-consuming, tedious, and expensive, because from the extraction of the stone to have the whole analysis can take several weeks, and we need to have very faster treatment in order to avoid relapses. So basically, as soon as possible, would be nice to be able to do this. So basically, talking with people from urologists in France and in different world persons, they have been saying, okay, if we have this process that give us a lot of information regarding the composition of the kidney stones, only using the visual information of the surface and the section of the image, would it be possible to actually analyze the stone directly in the endoscope, like when we're doing the extraction and the polarization of the stone using the laser? So basically, with this question, we started talking about possible ways of doing this, and since we are experts in our groups in Lorraine and in Mexico, analyzing endoscopic video images, we say, okay, maybe it could be possible to provide a very good estimate of the class of the kidney stone using only endoscopic images. Just to give you some context, there are many different kinds of kidney stones, about 21 classes. But here I am showing the ones with the highest incidence, basically those that are calcium oxalates, basically what we call Orjuela and Wetherite. Some of the others are uric acid, estrubite, brushite, and cysteine. These are the stones that have the highest incidence. And in the following slide, I am showing some of the images of the Wellcome cut, which are commonly also known as Orjuela and Wetherite, as well as uric acid. For example, these are three cases, and we also have estrubite, brushite, and cysteine. And we can observe that we have both surface and section images. Both of these images are used for classification when using the morphoconstitutional analysis, and the visual information is very important. So as you can see, there are different ways. For example, brushite has these patterns here in the section. Sometimes, depending on the color and the illumination, brushite and cysteine can be confused with each other, and this can also happen between Wetherite and aciclovir, for example. So it's very difficult, and many works have been proposed. And for example, there is a work by colleagues from University of Barcelona that have proposed to identify kidney stones using an apparatus with a very highly controlled elimination conditions. As you can observe, this is very nice and everything because you have very high control of the illumination and the quality of the image. But unfortunately, you don't always have access to this information, as we'll see later. So basically, the idea will be to have these endoscopic images, okay? But as you can see, the endoscopic images sometimes can be worse because we can have confusion between acidic and watery, which is even worse. So for humans to do this is very complex, but some colleagues from France working with Michel Dodona, with us as well, for example, Dr. Vincent Estrade, he has been working and pushing this idea for some years now, like about 5 years. For example, one of the studies he did was a concordance study between morphoconstitutional analysis using ex vivo images or microscopic images, if you want, and in vivo images or using endoscopic images. Basically, this table is coming from one of his papers from 2020, and basically he's describing the different types of kidney stones. We can see here that the number of good matches between, for the same specialist, the person that will be doing the morphoconstitutional analysis will find that the number of matches is very high for both endoscopic images and microscopic images for many of the classes. For example, most of the classes is very high. It's only a distributed broadsheet, as I was mentioning before, that's very difficult to classify for a person. So basically what this study demonstrated is that it's actually possible to have both methods in tandem and use it for the classification. So basically it's showing that endoscopic images have value for doing morphoconstitutional analysis, basically validating the idea that we have. So basically, endoscopy, as you know, is as you may know, is an apparatus that lets you go inside of the body, basically introducing a tube with a camera on the tip in order to analyze different parts of the body. It's usually used for analyzing, for example, gastroscopy, colonoscopy, for looking for tumors and this kind of thing. But it's also very used for urology, to introduce an endoscope in tandem with a laser or other instruments in order to remove the kidney stones. It's very interesting. So basically, we can, through the endoscope, we can introduce lasers, we can introduce baskets to remove the kidney stones, and many different tools. And basically, what this enables in the operating room is to actually see inside of the body, inside of the kidneys, and look for the kidney stones that we want to remove. It's a very complicated process. I myself, I would been able to attend some of these operations are very nice work what we have in terms of technology, very different, many different kinds of equipment inside. So it's very difficult to actually try to do the morphoconstitutional analysis. We wanted to do it endoscopically. And also we have different ways of, and this is a part of the motivation for this work, we have different ways of extracting the kidney stones. We can either use the ureteroscope, introducing a basket. When the size of the kidney stone is sufficiently small, we can remove it using a basket, which is very time consuming because you have to introduce a basket and then remove the kidney stones, introduce the basket, remove the kidney stone, and so on. So it's very time consuming. And the other option is introducing a laser, and the laser using a technique called dusting, which basically you set the laser to a certain frequency, to a certain settings in order to pulverize the stone. Basically, you have different techniques to move around. I will show this in the next slide, and then you can start pulverizing the stone. So basically, at the end, you have only powder. Sometimes you can also have fragments if it is not possible to remove it, but at the end, you will have some powder that will be very small. That is what it's called dusting, because at the end, you have some dust that can drain naturally through the body. So basically, we have this image from the CT scan, X-ray. So basically, you have this stone which has a certain size. After the dusting process, you will have dust of less than 1 millimeter. So basically, dusting has some advantages because it's less invasive. The operations are quickest to perform. However, we have the disadvantages of lower stone-free rate because some of the stones might remain and then grow again. And the most important part for what we care about here is that since the stone is completely pulverized, we'll have less information for the morphoconstitutional analysis because we lose the morphological information for doing the diagnosis, but also it has been demonstrated that the laser can alter the components of the biochemical composition, and that it can also bias the biochemical analysis. So this is problematic. So this is an excellent opportunity for doing in vivo categorization of kidney stones for diagnosis purposes. So basically, the idea will be to do that diagnosis directly during the endoscopic intervention. So basically, this work belongs to the endoscopic video analysis. and to the diagnostic decision support systems, basically, that needs to be done in real time. Very quickly, what we have done so far is that we have put this system in Masi, in which we have some data sets of ex vivo images and images. And we have been working very closely with people from Bordeaux, Universidad, and more recently with people from Masi, in order to collect data sets of endoscopic images. Basically, here I'm showing some of these examples. For example, they have been acquired with Olympus, Richard Wolf, and Storrs endoscopes, and we have certain numbers of images that we have acquired. And we have been using feature extraction techniques using deep learning, techniques such as data augmentation, transfer learning, and basically we're testing different models to determine the quality of the classification that we can obtain through this process. So basically, what is interesting if we compare traditional deep learning, machine learning methods with deep learning methods, we can see that we can have very high precisions for both surface section and even more when we combine the images. What we call mixed here, we can have up to 98% of accuracy for a few samples. So this is encouraging results, but obviously we still have a lot of work to do. For example, if we take this AlexNet model, which is a not very deep learning model, we can see that this is kind of visualization called UMAPs that enable to see images in a very low dimensional space to see how the different images are being separated. Basically, we can see that, for example, neither section or surface images are good enough for doing a good classification, because if, for example, we have Struvit and Brushit, as we knew that they are problematic because they are very easy to be confused with each other. The same way Wewelit, the section, we can see that when we combine the images, we can have better results, but we still have problems between Brushit and Struvit for AlexNet because the model is not deep enough. This is in accordance with agreement with the recent work by Banson and Strat, in which he demonstrated that a person will do the same mistakes. And this is due to the limited capacity of this model, but if we do something with a deeper model, we will see that we can get a better results, the result that I was showing before with a 98% of accuracy. This is some of the GradCamps or activation maps used for demonstrating how the deep learning models actually classifying these images, and we can see the different scores here. Basically, we can get very nice scores for most of the images. So we can see that this can be applied clinically. Obviously, we still need some work to do. For example, something that is very important is that, for example, many researchers have demonstrated that it's very difficult to generalize. For example, if we train a model using some images from a Storrs endoscope or a certain illumination, and we want to use it with a different hospital with a different endoscope, deep learning methods will have problems to generalize and to work well. So basically, for that, we need to collect more data and to use more advanced techniques. So basically, future work, some of the stuff that we want to do is increasing the number of images, obtaining images from different classes that we don't have currently, capturing images with different uteroscopes, and we also want to include, for example, Mexican institutions in order to get more data. But so far, for the moment, we have been working with people from Centre de Recherche Hospitalière de Nancy, specifically with Professor Jacques Hubert and Dr. Jonathan Elves in Nancy, to get more images, to have a process of doing a more thorough work in order to collect more data and to have methods that are more robust and able to generalize. We also have some ideas of because the way that the morphoconstitutional reports are done, we also have some ideas about generating reports in order to make it more understandable for the doctors, basically. And we are very lucky to have Professor Michel Dodon as part of our project, because he is one of the biggest experts in morphoconstitutional analysis in the world. I also want to thank my team, basically Professor Christian Doll in Nancy, which is working very closely with me. We have some PhD students in collaboration. We also have Dr. Jean-Luc Guéant, who is leader of the nutritional biochemistry lab in Nancy, basically the lab that it takes care of the analysis and doing the biochemical composition analysis. We have Jacques Hubert, which is the leader of the service of urology in Nancy. We have, of course, Michel Odon, Dr. Jonathan Delbese, who has been working, he's a surgeon, and he has been working, collecting data, extracting, and working on the protocols for this. We also have some master's and PhD students and interns working on these projects for master's students, 2 PhD students, one working on classification and continual learning. Basically, this idea of being able to learn continuously with the same data, because machine learning models are not static. They need to keep learning and to adapt into these changes. And we also have Daniel Flores Araiza, who is a PhD student in our group working on explainability methods, because we also want to be able to explain why the deep learning methods are doing the certain decisions, and also explaining with texts in a way that doctors can understand. So thank you very much. I also want to thank the EMBS Chapter Development Committee of 2022 for letting me to give this talk. And these are my contact details. I'm here in Mexico, Tecnológico Monterrey in the Guadalajara campus. You can follow me on Twitter in this account. And you can see my projects and my collaborations in my website here, or in the website of the faculty. We also have plenty of opportunities for master students and for PhD students with full scholarships. And we have a lot of collaboration with different parts of the world to have double diplomas and these kind of things. Yeah, thank you a lot. Have a nice day.
Muy buenos días con todos. Soy David Rivas, miembro de IEEE del capítulo MBS Ecuador. El día de hoy, al conmemorarse un año más de IEEE en nuestro IEEE Day, quiero compartirles la charla Procesamiento de señales cardíacas en casos de mapeo óptico. Para esta charla vamos a seguir la siguiente agenda, que vamos a tener una introducción, una problemática, explicar un poco lo que es el mapeo óptico, cómo procesar las señales, y tendremos un espacio para conclusión. Bueno, vamos a iniciar esta charla mirando qué es lo que nosotros tenemos aquí como problemas o como una introducción a este tema. Primeramente, nosotros queremos mirar a lo largo de la historia lo que es la salud de las personas. Al hablar de la salud de las personas, nosotros vamos a ir mirando a lo largo de la historia cómo muchos sabios, cómo muchos científicos dentro del área de la medicina y demás han ido evolucionando técnicas para garantizar la salud de las personas. Y con estos incrementos de técnicas, de métodos y demás, se ha ido incrementando lo que es la esperanza de vida. A lo que llamamos esperanza de vida es hacia cuántos años nosotros podemos llegar a vivir. En la actualidad, nosotros tenemos una esperanza de vida que sobrepasa los 80 años en el caso de mujeres y de los 75 hombres en el caso de hombres. Muy bien. Dentro de esto nosotros podemos mirar que hace algunos años nosotros veíamos que no existían gran cantidad de enfermedades cardiovasculares, o se detectaban ya en casos cuando tenían una presencia ya muy prevalente de la enfermedad. Pero en la actualidad, con esta esperanza de vida más larga que estamos teniendo, esas enfermedades se vuelven a ser mucho más notorias. ¿Por qué? Porque se presentan en personas, principalmente en adultos mayores, pero sin descartar que también aparecen en toda la población. Bueno, para poder identificar estos casos, se han generado distintos tipos de metodologías, y uno de los principales elementos que se pueden encontrar dentro de síntomas o signos que nosotros podemos encontrar dentro de este tipo de enfermedades cardiovasculares son las arritmias. ¿Qué son estas arritmias? Son puntos de mal funcionamiento del corazón, donde los músculos dejan de estar en sincronismo en su movimiento, produciendo estos desfases que podemos mirar por aquí y no tener nuestra frecuencia cardíaca tan bonita o tan simétrica como la tenemos en la actualidad. Bueno, ¿qué se ha hecho en la actualidad para nosotros poder diagnosticar estas arritmias? Estas arritmias que se presentan en varias personas a nivel mundial y son una de las causas de muerte de las enfermedades cardiovasculares más frecuentes en el mundo, nosotros hemos visto que necesitamos formas de poder diagnosticarlas, de poder visualizarlas. El primer elemento que nosotros podemos observar han sido nuestros electrocardiogramas clásicos, que sería la gráfica de nuestra frecuencia cardíaca, pero ahora se están iniciando con nuevos procesos o nuevas metodologías para lo que es este diagnóstico. Uno de estos casos son los registros intracardíacos experimentales, tal es el caso del mapeo óptico. En este caso, en el mapeo óptico, nosotros vamos a tener la siguiente metodología, la cual es la inserción de una cámara hacia el corazón, donde se va a poder visualizar una superficie corta, donde vamos a poder mirar cómo se encuentra, o registrar, perdón, cómo se encuentra el comportamiento eléctrico de la superficie del mismo, y de esa manera poder encontrar la zona donde no se está polarizando bien el músculo, y de esa manera poder identificar el punto donde se está generando la arritmia. Entonces nosotros tenemos un procedimiento en este sentido que lo podemos visualizar. Como le hemos dicho, esto es un proceso experimental, el cual nosotros vamos a partir de ello para poder procesar la información. Como vemos, es un corazón ex vivo, se lo coloca en un sistema de adquisición de imagen, como lo podemos ver. A partir de esta adquisición de imagen registramos un video, y ese video es el que nosotros vamos a proceder a procesar. ¿De acuerdo? Entonces nosotros vemos aquí cómo está nuestro corazón, cómo lo están colocando para la toma del video. Este punto que nosotros vemos aquí es bastante interesante. Se coloca una luz polarizada para poder identificar el movimiento en este caso, y lo que se hace es el registro del mismo a través de este video, que es lo que nosotros vamos a tener aquí. Muy bien, entonces, a partir de este video que nosotros lo acabamos de adquirir aquí, vamos a extraer la información. Para poder extraer la información, nosotros vamos a seguir la siguiente metodología, la cual primero corresponde a la evaluación de filtros de tipo FIR y tipo IR, para ver cuál se adapta mejor para nuestro sistema. Luego un filtrado temporal, espacio-temporal, y espacial y espacio-temporal, donde nosotros vamos a poder comparar no solo a la imagen como un conjunto de señales, sino como un video total, donde nosotros vamos a poder procesarlo en 3 dimensiones. ¿De acuerdo? Esto de decir 3 dimensiones, estaríamos hablando de X, del espacio XY, y una componente que sería el tiempo. Y finalmente nosotros vamos a hacer un análisis de componentes principales y componentes independientes para poder suprimir mayor cantidad de ruido de nuestro video y poder tener una información mucho más clara de cómo se encuentra nuestro sistema. Bueno, esa es la primera presentación que tenemos de la película. Esta película ha sido procesada y nosotros la podemos ver primeramente en un plano temporal, ¿no es cierto? Un número de muestras en amplitudes. Esto queremos decir que estos son los puntos de polarización. Si podemos verlo aquí, tenemos una parte del patrón cardíaco, que podemos ver nuestra frecuencia cardíaca, mientras que acá tenemos cómo se comportaría la superficie del corazón, tomando como muestra una parte de la película, un fotograma, y nosotros podemos verlo cómo se vería. ¿De acuerdo? Entonces tenemos por un lado la parte temporal y por otro lado la parte espacial. Aquí nosotros tenemos otra muestra de una película, pero vemos que tiene aquí mucho movimiento. A esto nosotros lo vamos a analizar luego, porque esto es el movimiento propio que tiene el corazón. En la primera gráfica que nosotros habíamos visto es un corazón que se encuentra prácticamente sin movimiento, mientras que aquí ya sería un corazón que se encuentra con su movimiento natural físico al realizar el bombeo, y por eso nosotros vemos que tiene las muestras o las señales mucho más movidas. Es más o menos como cuando tomamos una fotografía que vemos que se mueve, o el video movido, ¿no es cierto? Entonces eso también va a afectar nuestra medición. Bueno, tomando esta consideración, como al ser una película, al tener elementos electrónicos que nosotros estamos utilizando, hemos utilizado primero una transformación de tiempo a frecuencia. Eso nos permitió mirar o localizar esta frecuencia que aparece aquí. Como estos videos fueron obtenidos en un hospital de Madrid, entonces la frecuencia que nosotros tenemos por aquí es cercano a los 50 Hz. Entonces vemos que esto es prevalente en todas las películas y este es el primer filtro que nosotros vamos a utilizar para poder eliminar este ruido producido por la red eléctrica. A continuación nosotros vamos a tener un experimento que se basa en la utilización de los filtros IEEE, donde hemos podido evaluar desde el orden 1 hasta el orden 25. En este nosotros podemos ver cómo vamos suprimiendo ruido de la imagen principal que tendríamos, que sería la que tenemos acá hasta el fondo, hasta llegar a un momento de saturación, donde ya no vamos a poder filtrar más, ¿de acuerdo? Ya saturamos el filtro. Y vemos cómo vamos mejorando las condiciones de esta señal. En este caso estamos utilizando un píxel central, es decir, un píxel central de la película a lo largo del tiempo. Por eso nosotros vemos la amplitud que tiene, la dimensión y el tiempo y el número de muestras. Acá nosotros estamos haciendo un ejemplo similar en otro píxel y vemos cómo vamos mejorando. Si nos fijamos en las crestas, principalmente, nosotros podemos ver cómo se van redondeando y vamos teniendo la eliminación del ruido. Por otra parte, vamos a hablar ahora de lo que serían los filtros FIR. En este caso estamos evaluando de orden 2 a orden 256. Como vemos en los orden bajo, se empieza a tener todavía mucha presencia de ruido, pero según vamos subiendo ya las señales van mejorando, pero van a llegar un instante de una sobresaturación o un corte en la señal por un sobrefiltrado. Con esto nosotros hemos podido evaluar estos dos tipos de filtros y podemos mirar que un orden de un filtro FIR de orden 9 se equivale o tiene cierta equivalencia con un orden de un filtro FIR de 256. Si podemos ver en las gráficas se comportan de igual manera y en la presentación del filtro igual. Ahora, ¿cuál es la condición para poder seleccionar el uno o el otro? En este caso ya son los costos computacionales. Utilizando un filtro de orden 9 va a ser mucho más rápido que un filtro de 256. Bueno, y aquí nosotros tendríamos cómo se estaría comportando nuestro filtro. Podemos ver la película, cómo se está moviendo, cómo se va presentando y vemos aquí la presencia de uno de los latidos. Como vemos, los dos filtros se comportan muy similar y el ruido y esta sería nuestra película original y vemos que con el filtrado ya estamos mejorando y estamos obteniendo mayor información y estamos viendo que hemos podido localizar cuál sería el comportamiento del mismo. Bueno, ahora vamos a la siguiente etapa que les había mencionado, el cual sería la experimentación a través de filtros de mediana. El filtro de mediana lo que me va a permitir es realizar un análisis de el punto de medición con respecto a su alrededor. Entonces aquí me va a permitir tener una ventana de análisis entre un píxel y otro píxel, permitiendo tener un análisis de A con A o de A con B. Es decir, tomar todos los bloques, todos estos frames, uno a uno, hasta presentarlo como un solo paquete de información y poder procesarlo todo como un solo paquete de información. Entonces empezamos primero con un análisis temporal. ¿Qué quiero decir con el análisis temporal? A lo largo del tiempo. Con el siguiente, con el siguiente, con el siguiente. ¿De acuerdo? Entonces vamos viendo cómo se van comportando los que siguen, o podemos colocarnos en un punto y ver cómo se comportaron los de adelante y cómo se comportaron los de atrás. Y de esa manera nosotros poder evaluar. Si nosotros nos fijamos de aquí desde el orden 1 hasta el orden 99, vemos en las crestas cómo van cambiando hasta llegar a un punto donde se redondea, pero si nos fijamos en la parte superior, nosotros vemos que se corta, se trunca. Entonces ya estamos sobresaturando y lo mismo pasa en la parte inferior. Entonces nosotros podemos ver de manera experimental cuál sería el orden del filtro que nos puede servir. Por otra parte, vamos ahora a mirarlo desde el punto espacial, es decir, en un solo frame, en un solo fotograma, un píxel y ver cómo se comportan los de su alrededor, es decir, con los vecinos. Y de esa manera nosotros generamos una ventana, partiendo desde un 1 por 1 que sería un solo píxel hasta una ventana de 21 por 21, es decir, una ventana muy grande de muchos elementos que tendríamos aquí adentro. Y de igual manera, nosotros vemos en las primeras ventanas cómo vamos teniendo la presencia del ruido hasta llegar al número mayor del filtro, donde de igual manera tienden a trucarse, pero va mejorando mucho más la señal. Para el tercer experimento, lo que hemos hecho es juntar los dos, analizarlo tanto en el tiempo como en el espacio. Entonces, juntar todo en un solo bloque de datos, un solo bloque de información, y desde esa manera poder analizarlo. Por eso aquí hablamos de rangos, de ventanas y con respecto al tiempo. Y nosotros miramos aquí cómo ha mejorado muchísimo la señal. Podemos ver incluso cómo van mejorando cada uno de estos grupos y no existe mucho trucado en la señal y la señal se va presentando de mejor manera. Entonces, de esta manera nosotros hemos llegado a tener que el filtro de orden 50 era el que mejor prestaciones se tenía. Si nosotros vemos aquí, ya es la señal cardíaca que nosotros habíamos visto anteriormente, ya muy presente, muy prevalente. Acá de igual manera nosotros vemos cómo los flancos van mejorando, pero sin duda el filtro de mediana, ese espacio temporal de 9 por 29 es el que mejor forma me da a mi señal. Entonces, de esta manera nosotros hemos hecho una comparativa en estos frames, cómo se comportaría cada uno de ellos. Si nosotros vemos aquí toda la película, hay todavía mucho la presencia de ruido. Con el filtro de medianas se mejoró, pero todavía hay zonas donde no se ve muy bien, pero ya con el espacio temporal se ve mucho mejor. Entonces hemos tenido ya una mejora. Y de esa manera nosotros podríamos verlo aquí en la comparativa como lo habíamos hecho en el caso anterior. Nosotros vemos cómo aparecen cada una de nuestras señales. Aparentemente aquí nosotros no vemos mucho el efecto, pero sí vemos ciertos rasgos que la señal se va suavizando y principalmente estos espacios donde ya se quedan fijos, ya no vemos tanto la presencia de ruido y vamos viendo los puntos donde nosotros tenemos el interés de visualizar. Y vemos que se presentan de una manera muy interesante los resultados de la aplicación de este filtro. Nuevamente, del filtro original que nosotros tenemos aquí al filtro que hemos logrado obtener, estamos obteniendo mucha información y muy importante. Ahora, si nos fijamos hasta aquí, seguimos manteniendo ruido. Entonces, para esto vamos a ocupar dos técnicas adicionales, las cuales son, en este caso, el análisis de componentes independientes y el análisis de componentes principales. ¿Cuáles son las características de cada uno de ellos? En este caso, nosotros vamos a hablar primeramente del análisis de componentes principales. ¿Qué es esto? Toda esta señal que nosotros acabamos de ver aquí, o estas señales que estamos utilizando, son la composición de varias señales. Entonces, a través de esta técnica las podemos dividir. Si nosotros nos fijamos, la primera componente que tenemos aquí tiene prácticamente gran parte de la información. Incluso si nos fijamos en este punto superior, realizo una compensación. Aquí yo pierdo información y tengo una compensación. Mientras que en los otros elementos yo puedo decir que se encuentran ruido. Entonces, al aplicar esta técnica, yo puedo suprimir todas las componentes a partir de la segunda componente y no perdería la información, como lo tengo en este caso. Mientras que las componentes, y vemos como aquí nosotros tenemos la información. De acuerdo, aquí cada uno de estos pedacitos sería ruido. Mientras que en el caso de las componentes independientes, cada una forma o conforma esta señal, pero no tienen ninguna relación entre ellas. En el caso anterior, en componentes principales tenemos una ortogonalidad, mientras que aquí no tienen ninguna relación entre ellas. Problemas que tenemos aquí, que al ocupar esta técnica podemos captar partes de la señal muy específica. Como vemos aquí, tenemos un flanco, acá estamos viendo el flanco del otro pico, o podemos ver por acá el flanco de otro pico y demás. Entonces, con esta técnica se volvió un poco complejo poder identificar cuál era ruido y cuál no. ¿Por qué? Porque cada una se especializaba en una zona. Y de esta manera, nosotros vemos cómo tenemos aquí nuestra gráfica, y de esta manera nosotros se pudo identificar que en este caso, la técnica de componentes principales fue mucho mejor que la de técnica de componentes independientes, pues al suprimir una de las componentes, como nosotros vemos aquí, se generaron estos bytes. Es decir, sin querer, podríamos decirle, suprimí información. Mientras que acá pude obtener una señal de mejor característica. Y aquí nosotros podemos ver una comparativa entre las dos técnicas de componentes principales y de componentes independientes. Si nosotros nos fijamos, en algunos de los casos vamos a tener presencia de mayor error o de saturación en el caso de que nosotros hemos retirado alguna componente que tenía mucha información de la señal. Finalmente, nosotros vamos a analizar un elemento que les había mencionado al inicio de la presentación, el cual era el artefacto de movimiento. ¿Qué era ese artefacto de movimiento? Ese movimiento que va a tener el corazón de manera natural. Ese movimiento que nosotros lo sentimos cuando estamos relajados, que es bastante lento, y cuando estamos emocionados o cuando estamos con el momento de hacer deporte y demás, que es con mucha fuerza. Esto también va a tener una relación al momento de realizar nuestra experimentación. ¿Por qué? Porque le estamos tomando una señal de video, una señal óptica. Y esta señal óptica lo que va a realizar o lo que va a adquirir también va a ser este movimiento. Entonces se han realizado dos experimentos adicionales. Un experimento adicional, el cual es la evaluación del factor de movimiento. En este caso tenemos el factor leve. Como vemos, en el caso anterior nosotros teníamos prácticamente sin movimiento. Sí, vemos que la información se encuentra en la primera componente. Estamos bien hasta aquí. Y el artefacto de movimiento se podía ir sacando de las otras componentes. De igual manera, nosotros vemos aquí con componentes independientes, pasa exactamente lo mismo que había pasado en el caso anterior. No pudimos realizar mayor supresión, pudimos buscar por ahí algo que se parezca al artefacto de movimiento, pero no estaba tan claro. Y nosotros podemos ver aquí cómo se encuentra nuestra información del artefacto de movimiento. Como vemos aquí, esta señal salió mucho más limpia, pero cuando yo retiré una de las componentes, vemos que aquí generé unos picos que estoy suprimiendo información. Entonces, lo volvemos a comprobar. Por otra parte, vamos ahora con el movimiento moderado. Ya en las gráficas aquí con el movimiento moderado ya están un poquito más deformes. Es decir, ya no tengo tanto los patrones muy definidos como los teníamos en los casos anteriores. Entonces, de igual manera, la primera componente sigue manteniendo información, mientras que en los componentes independientes vuelve a pasar el caso similar. Y en el caso severo ya aquí sí tenemos muchos problemas porque ya la información ya no lo tenemos solo en la primera componente, sino tenemos que combinar algunas de ellas. Y en componentes independientes, de igual manera, la información sigue desperdigada por algunos sitios. Aquí lo que nosotros hemos logrado es, en artefacto severo, es poderlo disminuir hasta un artefacto moderado o un leve, pero no se ha podido adquirir una señal mucho más limpia. Y de esta manera nosotros tendríamos aquí lo que serían ya prácticamente nuestros resultados en estos tipos de evaluación o de filtrado. Y nosotros vemos cómo se comportó nuestra señal final. Bueno, como conclusión de este trabajo, nosotros podemos mencionar que los filtros IR y los filtros FIR se comportan de manera similar en este tipo de experimentos, teniendo ciertas ventajas los filtros IR por sus características de menor coste computacional. Por otro lado, nosotros tenemos el filtro de mediana espacio-temporal, se comportó mucho mejor que los filtros temporales o espaciales, pues pudo incluir toda la información de nuestra película sin dejar de lado matices que tendríamos dentro de la parte temporal o dentro de la parte espacial. Y al final nosotros hemos visto que el análisis de componentes principales fue mucho mejor que el análisis de componentes independientes. O esta metodología podríamos decir que fue mucho mejor. ¿Por qué? Porque las componentes principales tenían una relación entre ellas y se pudo suprimir mayor cantidad de ruido. Mientras que en componentes independientes, cada una de las componentes como que se volvía muy específica o muy propia de una forma de la señal o de una parte de la señal. Porque al suprimirlo podía yo llevarme información que era importante de otra zona del análisis. Entonces aquí tendríamos nuestro filtrado final, donde nosotros ya tendríamos nuestra película lista. Si nosotros nos fijamos ya, tenemos una señal bastante pura bastante limpia que ya la podríamos utilizar. Cabe mencionar o cabe recordarlo que todos estos son experimentales, son ejemplos realizados en laboratorio. Esto todavía no se encuentra realizado en seres humanos, se lo ha realizado en corazones de cerdo principalmente, y es una buena aproximación a nuevas técnicas para poder localizar lo que serían estos puntos donde tenemos mal polarización en nuestro corazón, y de esta manera poder reducir las consecuencias de lo que tendríamos por causas de una arritmia. Bueno, no queda nada más que agradecerles a ustedes por su atención. Ha sido un gusto para mí poder compartir con ustedes estos momentos. Queda mi correo de contacto si existen alguna duda o alguna consulta, y celebremos lo que sería nuestro día de IEEE. Un gusto haber compartido con ustedes. Muchísimas gracias. Hasta una próxima oportunidad.
Hi, I'm Sueli Fleury. I'm a professor at the University of Brasilia. In this seminar, I would like to share with you a Brazilian innovation made by biomedical engineer in development and production of a mask with nanotechnology. In the advent of the world health emergency that was the pandemic, our research group came across a request from the health authorities in the central-western part of Brazil to solve a problem that was to come: the national storage and discontinuity of supply personal protective equipment masks. The group, which already had experience in the areas of development of technologies applied to healthcare, especially assistive medical equipment, accept the challenge. Because when a health emergency arises, and exemplified by the COVID-19 pandemic, for example, the health science, technology, innovation, and especially biomedical engineer need to uh, uh, need to be placed to respond efficiently and fast. The feeling of being able to save lives. But the question was how to impact, how to control, and intervene in the rise curve of COVID 19 contamination in the Brazilian population. For every day that passed, we lost loved ones. The nation was losing one more brave citizen. We decided, yeah, then we decided to make a call to Brazilian research, to the Privacy Initiative, to Brazilian entrepreneurs, and especially the civil society. In this moment, the concept of the four essential actors for all development of technologies was consolidated: the university, the state, and the privacy initiative, and finally the civil society work together. Here we have this product. For 2 years, the mask has been on a path of consolidation, a method in biomedical engineer in the connection with a translational research. So we began the strategy design. It was building in a way that we could accomplish that what is conceptually called closing a cycle. We crossed the valley of death. The strategies adopted and the success achieved were the result of a set of surveys. What is the solution? The construction and developing a new face respirator. The construction of a disruptive solution was made possible by the product we called Vesta. In the other two product, in the other to the product protect the individual for the contamination of the COVID-19, which has a nanometric structure, the research for nanotechnology with bactericidal and fungicidal viral inactivator properties is necessary. N95 respirators with filtering phase piece respirator or similar filters have a reduced capacity to filter particles, but there are approximately 0.1 to 0.3 micrometer in size. This is a problem because the COVID-19, the structure, nanometric structure. Taking this evidence into account, there is a need for a respirator capable of inactivating a new coronavirus and increasing the efficiency of standard N95 respirators. The use of nanomaterials in this kind of product can increase its effectiveness regarding the reduction of particle permeability. It was carried out through systematic review, show for us, and we came up with the some products. But in this moment, one very important decision, select made in Brazil and made in the product, the main element, the strategy for building new technology that promotes the constant nation and global ecological protection. The element tyrosine derivated from Trump shells is select. Tyrosine is a natural cationic polymer derived from tishing, with important characteristics for the use in a new technology, since it is biodegradable, biocompatible, no toxic, and antimicrobial activity. And special is a low-cost raw material. In addition to that, we value has a strategy to use the use of a family farming. We seek to strengthen this nation extractive area because it generates ecological impacts and promotes the generation of jobs. This was the first foundation of the project decision. After the dialogue with the nation industries was carried out, this was important so that we could adapt the concept of our product to the productive base already installed. Obviously, improvements and small adjustments the industrial production process were made without causing major financial and structural impacts in the industry that decide to be a partner in the project. The development of the proposal and the details with the confection, transport, sanitary clearance, and costs were the focus of discussion in developing analysis together with the private initiative. However, it is important to point out that the following stage, the biomedical engineer with the translation research work together because what, why, how work in resume in this figure here. The These stages, first translational phase, we called T0, conceptual formalization. The second technology phase, preclinical or no clinical testing, T1. Second technology phase, very. Oh, I'm sorry. T1, preclinical or no clinical testing. Third technology phase, human clinical trials. And the fourth phase, the Anvisa, the structure, the our Brazilian vigilance agency called Anvisa, registrations and incorporation into health system in Brazil here. The all phase working together, and we apply this style of develop research and develop solutions, the technology, working very close with the Anvisa registration, enabling industrial scale production. The activities proposed by this research project provide the consolidation of the translational phase of the research. It is important to note that the actions are not sequential but parallel. They must all happen in a coordinated way. Of course, changes will occur and changes will have to be made in line with regulatory and research outcomes, of course. But I believe the main differentiator of this process promoted by biomedical engineer was a continual adaptation of the development process. All things here is a complementary actions we apply. It is important to highlight this. This is a strategy the biomedical engineer needs to observe in the construction of technologies apply, in special to health area. Interact with regulatory agencies or that will interact directly with ethics committees in human research is a very important point too. All things in this simple diagram here for increase the whole research project, for increase the aspects we standard with the execution of the systematic review with the meta-analysis is a very important start point, and involving other national or international research groups. To increase the strength of data, we must incorporate into the development of your technology the use in active and the principle of mathematical modeling simulations too. For example, in my group, ex vivo trials, and they use platform organ-on-chip simulation platforms, which are models that extract important data that will guide clinical trials and minimize bias. Yes. And mainly to promote more safety research participant is a very important point. All this phase 1 and 2 reflect a good and safety for the research participant in here in clinical trials. And the clinical trials design, we build solid endpoints and outcomes with well-defined inclusion-exclusion criteria that align with the ethical process. This is a fundamental for us to perform the registration of the clinical trial in the registration platforms and work together with registration at the health agency. In this case, in Brazil, Anvisa. Mainly by publishing these clinical finds, has a way to publicize the results. It's very important you publicize and relate all results you obtain, because this is a very important for all others groups. And it is in this image that I close this webinar. I suggest two links, but in Portuguese. You can see two important reports about this project that we observe the important and exciting moment of science making. You take the shrimp, you promote the new technology, and you protect and save lives. Biomedical engineer was protecting these health workers by putting on a mask that protects against COVID-19. The product developed was a basis of an existing respirator in the market, with an additional and extra layer to structure the mask, and they use nanotechnology. With this junction of two technologies, we was developing a new technology. Approximately 40,000 units of the Vesta facial respirator were donated to health departments in hospitals and universities. And 2,000 units are already in industrial production to made available to health system. In this moment, I need to acknowledgement and IEEE chapter development committee, because it's a very important. Would you like to thank the committee for this opportunity? It is with this feeling and with the support of IEEE that we can together build a safer, happier, and more caring humanity for us who make and develop technology. Thank you.